All right, we're back. Now what we're going to do is we're going to work on some examples where we take this new equation and we apply it to some points. So write a vector equation for a line containing points A at 3, 5 and B at -1, -5. Okay? Well, let's bring the equation down. P equals point A plus some scalar multiplier of B minus A. Okay? B minus A, that's your head minus your tail. So we just take point A at 3, 5 plus K times, and we've got -1, -5 minus 3, 5. So that is 3, 5 plus K times -1 minus 3. Those are the two x values, comma, -5 minus 5. Those are the two y values, because remember, this is an x and a y, an x and a y. Simplify that. You've got 3, 5 plus K times -4, -10. And there it is. That's the equation of the line that goes through those 2 points. Let's do another one. Same instructions, only this time we're going to use the point A at 8, -1 and the point B at 1, 7. P equals A plus K times B minus A. So this equals 8, -1 plus K times the point B, which is at 1, 7, minus the point A, which is 8, -1. Okay, so this is equal to 8, -1 plus K times 1 minus 8, 7 plus 1. Again, combining the x's and then combining the y's. So this would be 8, -1 plus K times -7, 8. And that is the equation in vector form of the line between those 2 points. All right, let's dig a little deeper. Two vectors, AB and CD, are parallel if and only if there's a number K such that, now, look, this is getting very formal, but you'd kind of expect it in the honors section of this textbook. Two vectors are parallel if there's a number K such that, where's my pen? B minus A, so that's the head minus the tail of the first vector, is equal to K, some multiplier, of D minus C, that's the head minus the tail of the other vector. So, two vectors are parallel if and only if there's some number that makes these two things equal to each other. Okay? Let's take a look at one. Here's example Gene. Oh, no, I forgot something here. Sorry. Now, if that multiplier is greater than 0, the vectors have the same direction. Okay, so if K is a positive number, these are going in the same direction. If K is less than 0, they have opposite directions. So one's going one way and the other one's going the other way. And if K equals 1, they're equivalent, because then the head minus tail here equals the head minus tail there. Now, let's do an example. Okay, find a vector equal in magnitude. Okay, equal in magnitude. So what I'm going to be doing is multiplying by 1, because that'll mean equal in magnitude, but opposite in direction. So I'm going to be multiplying by -1, so it changes the direction of the vector. So find a vector equal in magnitude but opposite in direction to CD, where C is at 3, 5 and D is at 6, 10. So let's put that up. Point C is at 3, 5. There's point C at 3, 5. And D is at 6, 10. 6, 2, 4. Okay, so there's D. at 6, 10. And I will draw that vector. C is the tail, D is the head. So there's the arrow. Now, I want to be equal in magnitude, but going the other direction. So it's going to be the same length, but the arrow is going to be on the other end. Now, you'll notice it didn't tell you where to start this vector. Sometimes the problem will tell you where to start the vector, sometimes it won't. So we get to assume a point this time. Okay? So, here's what we're going to do. We're going to, let's do this first. B minus A equals K times D minus C. Now, B and A, that's going to be my new vector. So I've got B minus A, that's the head and that's the tail, equals K. Well, the K is going to be -1 because it needs to be opposite in direction but equal in magnitude. So -1. -1 is equal in magnitude. I'm just going to abbreviate that mag. And opposite, OPP, in direction. Okay, anyway. And we've got D, which is at 610, minus C, which is at 35. So B minus A equals -1 times 6 minus 3, 10 minus 5. So B minus A equals -3, 5. All right? Or B minus A equals the vector -3, -5. Okay, so now what I'm going to do is I'm going to assume a point. So I need to start this somewhere, so I'm going to assume A, some point A. And I'll just pick 5, 6. So 5, 6. 2, 4, 5, 2, 4, 6. So there's my point A. And that's going to be the tail of my new vector. And that was assumed. They didn't give it to me, so I can assume it. Make sure you check in the problems. Sometimes they give it to you, sometimes they don't. Now we have to calculate where the new point B is. Well, you could, look, guys, it's not that hard. If I'm going equal distance but opposite direction, I'm going to go down 2, 4, I'm going to go down 5 and left 3. So I'm going to go down 5, 2, boom, boom, and left 3. That right there, see that dot right there? That's going to be my new head. But I can't do it graphically, I got to calculate it. So I've got B minus A, which is 5, 6, equals -3, -5, which I got from right there. Oops. Okay. Notice I'm using point notation here. That's okay. So what I've got is the X value at B, comma, the Y value at B, minus 5, 6, equals -3, -5. Okay? So X sub B minus 5, comma, Y sub B minus 6 equals -3, -5. Now we'll split it up, just the X values. X sub B minus 5 has to equal -3, and Y sub B minus 6 has to equal -5. Okay? So that gives me X sub B equals 2, and Y sub B equals 1. So my new point B is at 2, 1. And look, guess where it is? Point B is, in fact, at 2, 1. So that vector that is equal in magnitude but opposite in direction is vector AB. there you go. And if we want, oh, it did say to write the equation. Fine, okay. No, it didn't say to write the equation, but let's do it anyway. Let's do it anyway. So now I want the equation of that line. So it wasn't asked for, this is just a little extra for you. So P equals A plus K times B minus A. Okay, so this is going to be equal to A is at 5, 6. Plus K at B is at 2, 1 minus 5, 6. So that equals 5, 6 plus K times 2 minus 5, 1 minus 6. And that's equal to 5, 6 plus K times -3, -5. So there you go. That's the equation of the line in vector form for AB. And that was just a little extra for you.